Hello. Once again, it's your favorite time of the week. It's the time where I go through one of the worksheets. So today we're going through worksheet 11. This is a very long worksheet. It has lots and lots of graph stuff. There is a mix of mechanical stuff here as well as more theoretical stuff. I will try to touch on the theoretical side of things a bit because I think it's important to know. It's good to know. It will help you going forward. But I'm sure many of you have come here at this point just to watch me pound through these algorithms so you can repeat them on your own and do them on an exam, and that's perfectly fine. Okay, so we're going to start with the first question. First question is on topological sorting. This is something that students often don't quite get. I think it's just because we don't emphasize it that much in the class. But basically, this question is kind of in two parts. First, we're going to give a topological sort, and then we're going to answer this question of, is the topological ordering of the graph unique? So are there multiple valid topological sorts? Okay, great. So there's two main ways that you can think of a topological sort. The first one is basically a dependency tree, and the second one is a reversed post-order traversal. So let's look at the dependency tree first. What does that mean? So you may have heard someone say something along the lines of a topological sort. In order to do a topological sort, you need to kind of linearize the graph. Okay, what does it mean to linearize a graph? Basically, to linearize a graph means that all of the edges, all of the pointers on the graph nodes are pointing the same direction. So if we look here, we can see that this graph is mostly linearized because A is pointing generally to the right. A to B is pointing to the right, A to F is pointing to the right, A to E is pointing to the right, but then D is not pointing to the right, C is not pointing to the right. Okay, but remember this graph, we can move around the individual nodes as we wish. So I can basically redraw this graph such that everything is linearized. So just to do that, let's start with what we have. A points to B, A points to F, F points to E. This is all fine. The problem is here that from D, we have 2 pointers that are going backwards, but they don't need to be. So just kind of imagine what would happen. Try to imagine this in your head. If we took this D node and we just kind of moved it over this direction, right? We moved it over kind of to the middle of our graph. Right? The pointers that are currently pointing backwards, right? Or in other words, they're pointing the opposite direction that the pointers coming out from the A are, would start pointing the same way as the pointers coming out from the A node. So we'd end up with something more like this. Oops. Right? That's a very ugly C. C. Okay. So hopefully you can see that this graph that I've redrawn, it's the same graph as we have on the left. It's just I drew it in a slightly different way, such that now it's easier to make all of the edges look like they're pointing in one direction. Okay, this also makes it very easy for us to actually do our topological traversal. This brings us to kind of the second point. When someone says that a topological traversal is basically a dependency graph, what does that mean? It means that you don't traverse a node until all of its parents, all of its dependencies, in other words, are traversed as well. Okay, what does that mean? Okay, let's say we're doing a topological sort on this graph that I've just redrawn, starting at A. Well, the first thing we're going to traverse is A, so we're starting at A. Why can we start at A? Because there's nothing pointing at A, right? In other words, all of the previous nodes to A have already been traversed. It's a little trivial because A doesn't have any dependencies, but let's move on to the next one and hopefully become more clear. The next thing we could traverse is B, right? Why can we traverse B? Well, B has an arrow pointing into it. It has an edge going into it, but we've already traversed the node where that edge is coming from, right? In other words, we've traversed every node we need to traverse to get to B. Every node that comes before B has been traversed already. Okay, sure. What's another one to do next? D. We can do D because in order to traverse D, we need to have traversed all its dependencies. B is pointing at D, but we've already traversed it, and A is pointing at B, but we've already traversed it, so it's fine. Okay, so next we can traverse C. Same reason, because C is getting pointed to by D, and we've already traversed D. We cannot traverse E instead, right? I just traversed C, but we cannot traverse E instead. Why can we not traverse E? Because we haven't traversed F yet, right? And you see there's an arrow pointing into E. So we can do that. The next thing we can do is we can traverse F, because F has a dependency only of A, and then we can traverse E. Because E's dependencies are D and F, all of their dependencies are satisfied, therefore we can traverse E. Okay, so that's what it means. So you have to linearize the graph, and then you have to traverse it in order of its dependencies to get a topological sort. So this is a valid topological sort. The next part of the question also is, are there multiple topological sorts? And there are. You may have been able to tell while I was doing this topological sort, I first traversed A, and then I traversed B, but there's no reason I couldn't have traversed F first, because F also has all of its dependencies taken care of. So I could have gone FB, I could have traversed B, then F, I could have traversed B, then D, then F, then E, then C. It doesn't really matter, right? What matters is that every node that is being pointed to by other nodes, those other nodes have been traversed first. That's how topological sort works. And this also, I think, helps to elucidate the point. Another thing you may have heard is that you can't, there's no way to have a topological sort on a graph, right, that has a cycle in it. Why is that the case? Well, one thing is that this graph that I've just drawn here now that I've put an edge from C to A is no longer linearizable, right? You can't get all of the cycles pointed, or all of the edges pointing one way. And hopefully that makes sense, because if I try to, for example, redraw this arrow, which is pointing this direction, such that it's going to the right, that would necessitate, at least one of these arrows taking its place and pointing to the left. So you can't do that. But if we think of this in terms of the dependency tree, the reason that this graph now no longer has a topological sort is because basically there's no way we could ever take care of the dependencies of anything in this cycle, right? Let's say that we want to traverse A. Well, we can't traverse A till we've traversed C. We can't traverse C till we've traversed D. We can't traverse D till we've traversed A or B, and we can't traverse B until we've traversed A. So if we have a cycle that puts us in, quite literally, it puts us for a loop because we can no longer traverse the dependencies. Okay, that's one way to do it. Just for the sake of demonstration, there is another way to do a topological sort. So another way to do a topological sort is if you know that the graph is linearizable. In other words, if you know that there are no cycles in the graph, you can just run a DFS post order and then reverse the DFS post order, and that is the topological sort. So if we start a DFS post order from A, I'm going to do this pretty quickly. If you don't know how to do it a DFS post order, don't worry. I made a video yesterday about that. You can go watch, but I'm just going to bust this out pretty quickly. So if we start at A, we basically follow all the way down the chain down to C. We start popping things in a post order once they have no more children. So we get all the way down to C, we pop C. After we've done that, D cannot be popped because we still have to go to E. So we visit E, he has no children. Then we can pop E, then we go to D because now we visited all of its children. We go to B, we visited all of its children. We go to A, we can't visit it yet because it still is not a visited child. We go to F, we can pop it because it has no more children that we haven't visited. Then we go back to A and we can finally do A. Okay, this is our post order traversal. And if we just reverse this post order traversal, you will notice that we get a topological sort, right? One way you can also think of this is, if you remember, in the topological sort, you weren't allowed to traverse a node until you had traversed all of its dependencies. Well, in a post order, we're basically doing the opposite thing, right? You're not allowed to visit a node until you know it no longer has dependencies, right? That's why we go all the way down to C, which has no children, then we pop C. So in a lot of ways, this is kind of the reverse of what a topological sort is. And that's why you can do this and then just reverse the order and give yourself a topological sort. Okay, I hope that helps. Either way you decide to do it, you can find a topological sort that way.